In this video, we add the CMSIS RTOS to our project. CMSIS RTOS is a full-featured, real-time kernel for bare metal systems that manages tasks of threads along with time and memory resources. To add the RTOS component, open the Manage Runtime Environment window. From the CMSIS, choose RTOS Kyle RTX. This adds the RTX library and the related configuration file to our project. The RTOS needs configuration in the RTX config file. I can enter the settings directly in the C source file, but Microvision offers a configuration wizard where these settings are shown as options. For now, I just configure the RTOS kernel timer, where I set the input clock to 168 MHz. This is the core clock frequency of your system. The RTE manager updates the RTE components header file, and this file reflects the software components that you are using in your application. In main.c, the RTE CMSIS RTOS symbol from that file is used to enable the startup code for the RTOS kernel. At the same time, the empty while loop is removed. Therefore, our main.c file does not need modifications to start the RTOS. Well, of course, I want to do something with this RTOS kernel. We can use, for example, an RTOS timer to blink a LED. Again, we can choose a user code template. And for every key feature of the real-time kernel, a template is prepared. To blink a LED, we select the CMSIS RTOS timer. And this adds the file timer.c into my project. Let's take a look into this timer module. This module has an init timers function to start the timer. You can call this function everywhere in the application, but I'm adding this now to the main routine. Let's go back to the timer module. The init timers function creates two timers. Timer 1 is a one-shot timer, and timer 2 is configured as periodic timer with a 1-second interval time. Actually, this periodic timer calls the timer 2 callback function here. And now we are going to add code to blink the LED. And to do so, we can again use software components. In this case from the board support group. For many boards, interfaces to the peripherals are prepared. Depending on the board, you are getting various interfaces. This is a more complex board that offers many interfaces. But we are switching back to the ST board we are using. And I select the LED module. This adds under board support the LED module. Let's take a closer look to the source code. It configures and controls the I/O pins for the LEDs. The LED initialize function is the I/O setup. And with LED on and off, we can toggle the LEDs. The IDE even provides for all the modules header files that I can use. Just right-click and choose Insert Include File. For the selected components, the related file is listed here. The board led.h is the header file for the board support component. Now add the code to toggle the LED. And in the main routine, initialize this LED module. This completes our code and we can compile. But obviously I did an error. The editor shows you this even before compiling, but I did not pay attention to it. Let's compile again. And start the debugger. Now we verify our code. At the timer 2 callback, I set a breakpoint. And when I start my application, it stops at this breakpoint every second. There is also a timer in the status line that shows you the execution time. Now we remove the breakpoint and start again. On our board, we now see the LED blinking periodically at a 1 second interval. Such a blinking LED is a good sanity check of a correct system setup. The debugger offers kernel awareness for the CMSIS RTOS. Open from the debug menu, OS Support, System and Thread Viewer. Under System, the general configuration settings of the RTOS kernel is shown. For example, you can see the tick timer setting of 1 millisecond. Under Threads, you can see all threads that are currently active. The state shows you the status of your thread. The OS timer thread that runs our timer callback functions and blinks the LED is currently in wait state and is waiting for a mailbox event. You can see also the priorities and other parameters such as a stack load of the various threads. The ST Discovery Kit can be configured for using trace. When trace is configured and enabled, you may also use the OS Support Event Viewer window that shows you how the threads are executing over time. Again, you see all the threads that are running and you can identify when they are active. But as you can see, most of the time is spent in the idle thread that is executed when no other thread is active. Okay. I click on Stop in the Update screen and enable Task Info and Cursor. Next I click on one of the OS timer thread events. A red line appears. I place my mouse cursor over the next timer thread event. A window pops up and the delta time between the thread is confirming the 1 second interval with the value approached. This completes step 2 of our project. In the next step, I'm going to add the support for the USB memory stick to my application.